Sunil. You can hear me, right? Okay. So Arun is a certified principal statistical programmer with Inventive Health and has been using SAS for 10 years. He works extensively on cities SDTM mapping and ADAM standards. He presented a paper at PharmaSUG 2013, 2 papers at PharmaSUG 2014, and 2 papers at PharmaSUG 2015. Sunil is SAS certified SAS programmer working for Inventive Health, a statistical programmer. He has been using SAS for more than 9 years in a pharmaceutical industry. He has experience in different therapeutic areas and has worked extensively on CITES standards. He has presented 2 papers in PharmaSUG 2014 and 2 papers at PharmaSUG 2015. So welcome both of you.
Thank you. Okay, so the topic of our presentation today is what makes a statistical programmer different from a programmer. So someone who has a more basic understanding of statistics compared to someone who is programming but doesn't have better understanding of stats. And by the way, the guy in the yellow, that's me, and the guy in purple, that would be my friend if I go over my allotted time. All right, the agenda for today, the introduction, how come it helps my team, my organization, what is p-value, what is t-test, Box-and-Whisker plots, quartiles, and we're going to talk about some additional stats. All right, so how does it help me, my team, or my organization if I know stats? The first and the most basic point is I can help statistician by giving more comments when I review SAP. I can better understand data if I understand statistics. Obviously, I can catch mistakes at a much earlier level than waiting on the statistician to review and come back to me. I can understand if data makes sense statistically and it's not just a random variation. So yes, that's the slide which shows we all can drive without rules, with or without following rules, and similarly we can program with or without following stats. The point to note here is people can drive here without following rules, but what's going on is it's taking time for people to move from point A to point B. It's taking resource, they are wasting money on gas. That's exactly what happens if we program but we don't know stats. We end up finding mistakes in the last level. We end up spending more time towards the end, close to the database log. We end up asking for more resources from other teams and sometimes going over the cost of the project. All right, so what is p-value? I have asked this question to many people in interviews, and the concept I could come up with that p-value is something that it looks like a purple monster with red eyes, and I have got detailed answers. I've got less detailed answers like what is p-value? P-value is p-value, which is something to do with 0.05, and that was my reaction here. But all right, so let's go to the topic. So before understanding p-value, let's try to understand hypothesis. So what happens is once we write the SAP, we determine the test that would be used to calculate p-value, and then the next step is come up with hypothesis, which is null hypothesis and alternate hypothesis. Null hypothesis is something that says that there is no difference between placebo and drug. Alternate would be something that would say there is difference between 2 arms, drug and placebo. Level of significance alpha, that's something which is what we were talking about as 0.05. So basically, it could be different from 0.05, but for example, we've taken 0.05 here. So what is nothing but it's actually probability of rejecting null hypothesis. If it's true, if the value of probability is going down or is less than 0.05. And the graph here, the graph here shows the shaded area shows rejection is actually the p-value, where p-value is, it's a two-tailed test, so 0.05 would be 0.025 and 0.025 divided, but it basically shows if if p-value falls in the shaded area, that means we can reject null hypothesis, but if it falls under the non-shaded area, under the curve, that means we are not able to reject null hypothesis. We move on to the next slide. This is the algorithm, and pictures worth more than words. So what goes on is, when we start a clinical trial, we write SAP, we come up with something to determine p-value, which in this case, for example, we are taking t-test. We write hypothesis, identify claims that this will happen or this will not happen, and hypothesis will be null hypothesis and alternate hypothesis, and null is always HO and alternate is always HA. And once we determine the hypothesis, we gather information through clinical trial data. Once we have the data, we do some stats, and we plug in the formula in the t-test, and once we do that, we get p-value, and p-value helps us to make decision whether to reject null hypothesis or not to reject null hypothesis. And once we make decision, we summarize the result. Let's move on to next slide, and this slide basically summarizes everything what I just said, but I want to concentrate on the last 2 points, which says if we have a small p-value, which would be less than our alpha value, which is 0.05, for example here, that means it has a strong evidence against the null hypothesis. In case we get a bigger p-value, obviously we are unable to reject null hypothesis. Okay, one of the tests to determine p-value is t-test, and it's actually one of the hypothesis tests, and the way to know is if the value of the t-test is closer to 0, that means more likely we're going to reject null hypothesis. And I've taken an example here. So we have 6 students. They were given a math test, and they were given a weekend training actually. Before test, so 6 students, they were given a weekend session of test. So before giving that weekend session, they were tested, their scores were taken, and after giving them a weekend class or extra class, their scores were tested again. So what we do is we want to find out if the weekend test helped them to improve their scores or not. So we, according to our algorithm there, we come up with 2 hypotheses, null hypothesis and alternate. So null says that weekend class doesn't help students to get better scores. The alternate says it does help. So scores would not be same before and after. This is on the top is the t-test. When the output, it's a partial output. I just wanted to concentrate on this portion. Obviously, just the output just before this was showing that the mean difference is 7 points for students. So students have improved their score after taking that weekend session. They have improved their score by 7 points. So the question is can we assume that the weekend class helps students or not? Well, that's where our p-value comes in. So we see p-value is 0.0074, which means that, and let's assume that alpha was 0.05, and which means definitely that we can reject null hypothesis since p-value is less than alpha value, and we can assume that our alternate hypothesis is, we can reject the null hypothesis, our alternate hypothesis is true, that weekend class does help students. Moving on to next slide. From here, my friend Arun, you'll take over and
thanks,
thank you.
All right, can you hear me? Okay, great. So the next topic of our presentation is called Box-and-Whisker Plot. All right, now most of you would have seen this plot in your programming life, and many of you would have programmed it too using the box plot procedure. So before getting into the statistics and the details of what exactly a Box-and-Whisker plot is, I have two questions for you. Question number one, where is the box in this plot? Anyone? Where is the box? Go ahead. Give it a try. Yeah, the center one, right? Yeah, that's the center one. It looks like a box, so it must be the box. Yeah, that was an easy one, wasn't that? Okay. So here's the next one. Where is the whisker? I knew there would be a silence. Oh, you're right, exactly. So the two lines that you see here on either side, stretching from the box, one here and the one there, those are all whiskers. Okay, so now we know where the box is and where the whisker is. Let's get into some details. So what does it say? What does a Box-and-Whisker plot say? In a nutshell, it shows the distribution of data that we are trying to analyze. It says the values that we are trying to analyze, whether it is biased towards one end, towards the minimal value, or towards the maximum value. Or in other terminology, it's called skewed in Box-and-Whisker plot terminology. Okay, so we know it's going to show the distribution of data, but how exactly it shows the distribution of data? Well, it shows the distribution by using 5 basic statistics, and those statistics are the minimum value, the lower quartile, which is also called Q1 or 25th percentile, the median, which is also Q2 or 50th percentile, the upper quartile, which is Q3 or 75th percentile, and finally, the maximum value. So we have the 5 basic statistics that are represented on a Box-and-Whisker plot. Now I know all of you know what a minimum value is, what a maximum value is, but I know many programmers have confusion when it comes to quartiles, Q1, Q2, Q3, especially programmers coming from non-statistical background. So for the same reason, we're going to focus on quartiles on the next couple of slides. So what are quartiles? Well, quartiles are values that divide a list of numbers into quarters. It's simple. Now we have two terminologies here. One is quartiles here, and then there is quarters. So let me take an example. Consider a rope of definite length. Now if I want to cut this rope into 4 equal parts, what do I need to do? How many times do I need to cut this rope? I will have to cut this rope exactly 3 times. So here I go. With my first cut right in the middle, here's my second cut, and here's my third cut. And what do I get? I get 4 equal pieces of the same rope. Now let's apply the same logic to real numbers. In the first example, I have a set of 7 numbers right here, not in any specific order. So the first thing that we do before creating a Box-and-Whisker plot is to arrange those numbers in ascending order. So I'm putting them in order here. 3 is the minimum value in the list and 8 is the maximum values. Now I'm going to cut these numbers the exact same way I did with the rope. I'll take the middle value, which in this case happens to be 5, and that 5 is going to be the median of this list of numbers. It is also called Q2 or the middle quartile. Now I have 2 halves. On the left half I have 3, 4, 4. On the right half I have 6, 8, 8. I do the same thing with the left side. I cut it, the middle value is 4, which becomes my Q1, and on the right hand side 8 becomes my Q3 or the upper quartile. Now let's take a second example. In this example, I have more numbers. You see the list of numbers, it's not 7, it's 10. So I order it first, and then I try the try to find the middle number, but I don't have a middle number in this case because it's even set of numbers. So what do? What I do is I take the two middle numbers and average them out. I take the average of those two numbers, 5 plus 6 divided by 2, 5.5, and that is going to be my median, or Q2. And now coming back to Q1, it's the same. I take the left side and find the middle one. I take the right side and get the middle one there. So I have 3, 5.5, and 7 as my Q1, Q2, and Q3 respectively. Now let's take a look at the final example, putting it all together. In this example, I have a set of numbers here. I put them in order. I cut it into 4 equal quarters. And I see the quartile 1 is 4, which is right from here. Sorry, which is the average of these two 4s. And then Q2 is the average of 10 and 11. 10 plus 11 by 2, 10.5. And for the last one, it is 14 plus 16 divided by 2, which is 15. And again, what is the minimum value? 3, and the maximum value is 18. So I got my 5 basic statistics required to plot a Box-and-Whisker plot. So here's the plot. It's plotted against the x-axis. That's why you see it in the horizontal plane. Otherwise, you would see in the vertical plane. So I have my whisker starting at 3 because 3 is the minimum value. I have the whisker ending at 18 because 18 is the maximum value. And I have my Q1, Q2, and Q3 on 4, 10.5, and 15 right here. So there you go. Now, there are some additional information that a Box-and-Whisker plot gives. And those are called range and IQR, or interquartile range. Now, what is a range? Range is the difference between the highest value or the maximum value and the minimum value. So if you subtract the minimum value from the maximum value, you have the range. Similarly, the interquartile range is the difference between Q3 value and Q1 value. And finally, there are two additional statistics that I can represent on a Box-and-Whisker plot. One is mean. Now, mean is different from median. The way we calculate mean is different from the way we calculate median. So if I want to represent mean also in a Box-and-Whisker plot, I can do that usually by using the symbol plus. So that's where the mean is. And the other thing that I can represent is called outliers. If I don't want my outliers to be within the minimum maximum value range, and I want to represent that as separate outliers in my Box-and-Whisker plot, I can do that. And I can represent that using a small square box right here. Now, because I have some more time, I'll talk a little bit more on this. This is not a one-step process compared to the 5 basic statistics that I explained before. In order to get the mean and outlier value, you have to create a summary data set first. So it's a 2-step process. You can use the proc box plot first, and then use the outbox option to create a summary data set, and then use a second proc box plot, use that summary data set as input, and then create a plot that would look like this. Now we are opening it up for questions. Yes?
When you choose an outlier, what differentiates between making that the upper range of the maximum? Why would you say that's an outlier instead of a maximum? Make that decision.
Okay, so that decision is made by the proc box plot procedure. In the first, like I said, it's a 2-step process. In the first step, we use proc box plot, and then we use the out box equal to option in the plot statement. So what happens is it creates a summary data set, and if you look at that summary data set for every category, it will have set of statistics generated within the summary data set, like n, which is the total number, minimum, maximum, all the 3 quartiles, and if there are outliers in the higher region and in the lower region, that would be there, the minimum value, max value, everything will be listed for every single category. And then we use that data set as input to the next proc box plot. In this case, we don't use proc box plot data equal to option, but we use proc box plot box equal to option, and then pass in the summary data set that we just created in the previous step. So it knows what to read, what are the outliers, what is the minimum and maximum values, and the plot will be plotted accordingly. Great question. Any other questions? Yeah, go ahead.
Actually, a question for him.
Oh, yeah, sure.
Okay, so when you said that 0.05 is what determines significance,
As alpha and
it could be. Why do we do that? Why couldn't it be 0.06?
Oh yeah, it could vary. It depends on us what we want to set alpha value as. I just took 0.05 as an example.
Most people do that. That's done a lot.
Yeah, but that all, yes, I agree. Most of these experiments do have 0.05, but we can set it up different.
I think it's an acceptable range. If you bring it further down, like say
Yeah, that'd be a big
0.25,
risk.
it's very difficult to find evidence against the null hypothesis. The population,
Right.
the sample population will have to be extensively large in order to support
Yes.
that. And the
That's-
same happens on the other side also. If you make it about 10, then it's very easy to prove it wrong. So that's where we find the balance. So the statisticians will come up with that number that, depending on the analysis that we're trying to do, that this is the balanced number that we can consider for this specific analysis. Any other questions? Thank you so much. Thank you.
So thank you.